Myself, Sanmugh Sundaram, Professor Sri Ramakrishna Engineering College. This video is about semiconductor devices. This video covers diodes, its working principle and characteristics, regulated power supply, BJT, its characteristics, H parameters for CE, CB, and CC configurations, biasing circuits and their types, transistor as a switch, and transistor amplifier circuits. Coming to the basics of semiconductor devices, let us consider silicon. Silicon has 4 valence electrons in the outer shell. A stable atom will be having 8 electrons in the outermost shell, whereas isolators have 8 electrons. So almost they are stable under normal conditions. Whereas semiconductor, we have exactly 4 electrons, like silicon and germanium. They have 4 electrons in the outermost shell, and whereas metal has less than 4 electrons. If you see the energy gap, so here there will be energy gap between the outermost cell and the next inner cell. Similarly, between the next second level and between the third level, there will be energy gap. And all the electrons are bound to nucleus. Energy level, the more distinct the electron from the nucleus, the higher the energy state. That is, the outer cell will be having higher energy state. So energy level of electrons at outermost orbit is called valence band. Energy needed in electrons for conduction is conduction band. For example, we take the insulator. So here valence band, almost we know that there are 8 electrons. Or to move electrons from valence band to conduction band, we have to apply a large energy, approximately 5.5 electron volts. This much energy is required to release electrons from valence band to conduction band. The electrons in the conduction band are responsible for carrying current. Whereas in the semiconductor, we need 1.1 electron volt to move electron from valence band to conduction band. So somewhat lesser energy. Whereas metals, very less energy is required. So here valence band and conduction band, they overlap each other. So this is for insulator. You can see that the energy gap is indicated as 5 electron volt. So if you want to move electrons from valence band to conduction band, the electrons in the conduction band is only responsible for carrying current. So we have to apply energy greater than this 5 electron volt. And similarly for semiconductors, so the energy gap is around 1.1 electron volt for silicon, and it is 0.7 electron volt for germanium, and it is 1.41 electron volt for gallium arsenide. For metals, so the conduction band valence band overlap each other. So the energy required is very less. It is 1.6 into 10 to the power minus 19 joules. It's a very small amount of energy is required to move electrons from valence band to conduction band. Coming to the intrinsic semiconductor, so it is made of pure silicon. If you take pure silicon, so it has got 4 electrons in the outer shell. They are bound to nucleus. So in intrinsic semiconductor, pure silicon is used, and there will not be any impurities since it is a pure semiconductor. No charge carriers at exactly 0 degree Kelvin. At room temperature, there will be only few charge carriers. That is, number of holes will be equal to number of electrons and not suitable for electron devices. As it is, we cannot use this intrinsic semiconductor for creating devices. Coming to the extrinsic semiconductor, to increase the conductivity of the semiconductor, so we have to add a dopant, either a trivalent impurity or pentavalent impurity. If you are going to add trivalent impurity like boron, which will be having only 3 electrons in the outermost shell, this 3 electrons in the outermost shell will be paired with the electrons in the neighboring silicon, and one hole will be left. So that is called as hole. The holes will be the charge carriers in this case. If you are going to dope silicon with trivalent impurity. So we get a p-type material. So where holes will be the charge carriers. In the n-type material, so we'll be adding pentavalent impurity phosphorus. If you're going to add phosphorus, it will be having 5 electrons in the outermost shell. So 4 will be paired with silicon, 1 free electron will be left. So therefore, if you are going to add pentavalent impurity, electrons will be the charge carriers. So with P and N layers, we can form different devices like we can form diode if you are going to combine P and N region. So here with the two regions, if they are sandwiched, we get a diode. So it has got anode and cathode terminals. Anode is taken from P layer, cathode is taken from N layer. Then to form BJT, bipolar junction transistors, so we have to use 3 layers. So if you are going to use 2P and 1 layer, we get NP transistors. With 2N and 1P, we get uh, NPN transistors. So here in PNP, so the outer layers, the terminals are taken and they are collector and emitter, and the middle layer, the terminal taken as named as base. Similarly, NPN transistors. So from the two outer end regions, the terminals are taken, they are named as collector and emitter, and middle region, B region, it is called as base. Usually this middle region, base region will be thinner as compared to the outer layers. Thyristors, so with 4 layers, 2P and 2N layers, we can form a thyristor. So here, uh, so P and PN. So like this, their layers are combined to form thyristor. So from P layer, anode terminal is taken, from N layer, cathode terminal is taken, and from the P layer, which is common, which is near to the N layer, gate terminal is taken. Again, junction diode. So here, when P region and N region are sandwiched, we get a diode. So they are sandwiched. So usually P region, the terminal taken is called as anode, and N region, the terminal taken is cathode. So here at the junction, so the electrons in N region and holes in the P region, they combine here, and they here at this region, a depletion layer is created. That is, so electrons and holes, electrons from the N region and holes from the P region, right in this portion, they combine and form a depletion layer. So as a result, a barrier potential will be created, which will be around 0.7 volts for silicon, whereas 0.3 volts for germanium. So if the device has to conduct current, so we have to apply forward voltage at least equal to this barrier potential, or this voltage is also cut-in voltage, or also it is also called as threshold voltage. So now let us see how the diode works. In the forward biased condition, So anode is made positive with respect to cathode. So positive voltage is applied to anode, negative voltage is applied to cathode. If you are going to apply potential like this, so this negative potential will push the electrons from N region to P region, and similarly this positive voltage will push this holes into the N region. So therefore the electrons crosses this depletion layer and gets attracted towards positive terminal. Similarly, holes will move into this N region, gets attracted to the negative terminal. So therefore, there is movement of electrons. So the electrons are moving in this direction. This blue color arrow mark indicates the direction of electrons. This orange color indicates the direction of holes. So as a result, current will be flowing through the device. The current direction will be opposite to the direction of electrons. So the electrons are moving in this direction from left to right. Therefore, current will be flowing from P region to N region. That is from anode to cathode. So this is the circuit. So here the voltage source, forward voltage is applied, diode, and a resistance is the current limiting resistance. In this circuit, when forward bias is voltage is applied, so the current will be flowing through the device. So when it is forward biased, so it acts as a short circuit, and the current through the diode, forward current is given as saturation current multiplied by e to the power of Vd. Vd is the diode voltage drop divided by eta into Vt. Vt is the called threshold voltage or cut-in voltage minus 1. So the conventional current flow direction is from anode to cathode, and this is the symbol. Usually if you see a diode, so there will be a ring at the cathode terminal, so that we can identify the cathode terminal by locating the ring in the device. Coming to the characteristics, so let us see the characteristics in the forward operating region. Forward operating region, the diode is forward biased. So when the voltage across the device becomes equal to cut-in voltage, which is zero. 0.7 for silicon and 0.3 for germanium, the diode starts conducting current. As the current through the diode increases, you can see that the voltage across the device also increases, slightly increases. You can see here this line, it is slightly moving away from this vertical axis. So this from this point to this point indicates voltage drop across the diode. So here it is minimum, and whereas here it is large. So therefore, with increase in current, the voltage drop is increasing. Coming to the reverse breakdown region. In the reverse breakdown region, a cathode is made positive with respect to anode. So therefore, reverse voltage is supplied. The diode will not conduct. Only a very small leakage current will be flowing, and its magnitude will be very, very less. As you are going to increase the voltage, the leakage current also slightly increases, and at a particular voltage called as a reverse breakdown voltage, the device suddenly starts conducting current, and the reverse voltage at which the device starts conducting is called as a reverse breakdown voltage. So at this point the junction breakdowns and starts to conduct in the reverse direction, and no longer the device can be used, and the device never should be operated at this point. So always the device should be operated such that the reverse voltage is well below reverse breakdown voltage. So this is the diode. Vd indicates the forward voltage drop. This ring indicates cathode terminal. So this equivalent circuit is this. So actually diode has a threshold voltage of cut-in voltage of 0.7 volts for silicon, and this material also has some resistance close to 10 ohms, and the voltage across the diode is called as Vd. In some cases it is called as Vf. So in forward bias condition, anode is made positive with respect to cathode. The diode conducts current, it acts as a short circuit, and the cut-in voltage will be points on both. So it will be opposing the forward voltage. So only if the voltage, forward voltage becomes equal to or slightly greater than this, then the current can flow through the device. In the reverse bias condition, cathode is made positive with respect to anode. So therefore, the diode will not conduct current. So it is shown as an open circuit. And this is the barrier potential at the junction. Coming to the characteristics, that is, we'll see effect of temperature on characteristics. So in the forward operating region, so this curved red line, it is characteristics is at temperature equal to 25 degrees centigrade. This is less than this and this is greater than 25 degrees centigrade. So if you see here, if you are going to reduce the temperature or if you're going to operate the temperature below 25 degrees centigrade, so we'll find that this curve, it is shifting towards left, that is moving away from the vertical axis. This implies that the voltage across the diode, voltage drop across the diode is getting increased. So as the current increases, right, the voltage drop also getting increased. So as compared to 25 degrees centigrade, for lower temperatures, the voltage drop is found to be large for the same current. If the temperature is increased, then we find that the curve is moving closer to vertical axis. It implies that so the forward voltage drop is getting reduced. Similarly, in the uh, reverse operating region, so this is the curve that represents 25 degrees centigrade. So you can see here when the temperature is reduced, so here the breakdown voltage is getting reduced. So the device is likely to break down at lower voltage. If the temperature is increased, right, if the diode is going to operate at higher temperatures, then we find that the breakover voltage is getting increased. So, so this is how the characteristics vary with the change in temperature. And coming to the avalanche breakdown is a phenomenon that occurs in both insulating and semiconducting materials. It is a form of electric current multiplication that can allow very large currents within materials which are otherwise good insulators. It is a type of electron avalanche. For example, we take a material, for example, it can be an insulator, it is not carrying current. Suppose the temperature increases, temperature of the material increases, what will happen is the electrons will be liberated. So free electrons will be created because of the increase in temperature. The electrons gain energy and they try to come out from the valence band to conduction band. So these electrons are called as free electrons. They are moved to free uh, in the structure. So this for the electrons further it will be flowing and constituting current. Because of this movement of electrons, the current is flowing and as a result heat is also developed in the device. And this heat further it will liberate electrons and as a result, right, more and more free electrons will be produced and as a result the more current will be flowing. So this process continues and at a particular point of time the device starts conducting and that device will no longer be acting as an insulator. Similarly, in the case of diode, in the reverse breakdown region, the diode actually should block current. But when you are going to increase the voltage to breakdown voltage, So at that point, the current, their free electrons, more free electrons will be produced, and thereby the device starts conducting current, and thereby the junction will break down, and no longer the device can be used. And what we have to learn in PN junction there. So we have to know about forward and reverse biasing conditions, so how it works. Then you should know about the depletion region, why it is formed. Then you should know the reverse saturation current. It is nothing but the current that is flowing in the reverse bias condition. Then we should know about the equation for forward current. Then we should know about barrier potential and knee voltage, which is also called as cut-in voltage for silicon germanium. Then breakdown voltage is nothing but the voltage at which the device starts conducting the reverse direction. Static and dynamic resistance. Static is means the resistance, fixed resistance of the device, and dynamic means the resistance by the device in conduction. Similarly, parameters like forward current, peak inverse voltage is nothing but the reverse voltage that is applied across the device, power dissipation. So the power, how much power is dissipated in the device. Then we should know the applications. Diodes are used in almost all electronic circuits, in rectifier circuits, etc. And we should also learn about how to interpret parameters in datasheet. So datasheet has all the parameters corresponding to a particular device, like forward current, reverse current, then reverse breakdown voltage, forward voltage drop. All those things are provided by the manufacturer. Similarly, power dissipation, operating temperatures, range. So we should know how to understand the parameters from the datasheet. Next, we'll see about this device, bipolar junction transistor. In short form, it is called as BJT, the basics. So BJT is basically it is a three-terminal device. So we have two types of transistors, NP and PNP. BJT is a current control device. Terminals are emitter, base, and collector. So applications of BJT, it is used as a switch and also it is used as an amplifier. So it can be operated in three regions: cutoff, active, and saturation region. So three BJT configurations are common base, common emitter, and common collector. So commonly used configurations, common emitter. Biasing methods are base resistor, collector feedback, and potential divider. So this potential divider method is a common method. And bipolar junction transistor, it can be considered as two diodes connected back to back in series. For example, PNP transistors is equivalent to this circuit, right? You can see the two diodes, they are right in anti-parallel direction, they connected in series. So this P layer is emitter terminal, this P layer is collector terminal, and this middle region is base region. So usually this middle region will be a thin region. The two end regions merge to form a thin base. So the two regions, right, merge to form a thin base. The two types of transistors are PNP and NPN. So PNP you can see here. So collector region and emitter region are P regions, and base region is N region. So here usually the middle region will be thin as compared to the outer layers. So this is a symbol for transistor. So this usually arrow mark is placed in the emitter terminal. It is pointing inwards. Whereas NPN transistors, so collector and emitter are taken from N regions, base is taken from the P region, and this is a symbol. So here the arrow mark is placed in the emitter terminal, it's pointing outwards. So always the emitter current will be equal to sum of collector current plus base current. So there are three configurations. So one is common base configuration. So here, base terminal is common between input and output. Means input is applied between emitter and base. Collector output is taken from collector and base. Common emitter configuration is a commonly used configuration. So emitter terminal is common between input and output. Common collector configuration. Collector terminal is common between input and output. Let us see the operation of NPN transistors. So here there are two junctions. Here there is one junction N and P, and here there is one junction P and N. So there are two junctions. So here VB is the voltage applied between emitter and base terminal. So here the polarity is like this. So here if you are going to apply polarity like this region will be forward bias. So that is emitter base junction is forward bias. This junction is called as collector base. Whereas VCB is the voltage applied between collector and base, and for this polarity, this junction will be reverse bias. So when you are going to apply this voltage VBA, negative terminal is connected to N region, positive terminal is connected to base region. So now, because of this negative voltage, electrons will be injected from this N region into P region. So electrons will be injected. So we have to remember that the holes concentration is very much less as compared to that of the electrons present in the N region, because it's a thin layer. Number of holes will be less as compared to the number of electrons in the N regions. So now the electrons are pushed into this P region. Some electrons will combine with holes, and that constitutes base current. The remaining electrons will be pushed into this N region, that is into this region, and these electrons will be attracted towards the positive terminal of the source. And as a result, the electrons are moving like this, and few electrons are they combine with holes here, which will be constituting base current. So this is how the electrons will be flowing from emitter terminal to collector terminal. As a result, the collector current will be flowing like this, flowing in opposite to the direction of flow of electrons. So it will be flowing like this, from right to left. So this is how the NPN transistor works. If the base drive is increased, then in that case more and more electrons will be flowing in the circuit, and thereby more current will be flowing in the transistor. Coming to the modes of operation, so it can operate in three different modes. Cut-off mode, the transistor is in off state, both junctions are reverse biased. When it is operating in the active region, input terminals are forward biased and output terminals are reverse biased. When it is operating saturation region, the device will be fully conducting, both junctions are forward biased. So here the polarity is shown here. So that is the polarity of voltage that is connected across collector and base junction and base to emitter junctions for PNP and NPN transistors. Then coming to biasing, biasing is the process through which collector current IC is kept constant, withstanding the variation in beta and temperature. So the collector current is given by this formula, beta times IB plus ICBO. So collector to base current with the base terminal open. So the beta also, it depends on temperature, it varies with temperature. Also this parameter ICBO also varies with temperature. So because of this variation in beta and ICBO, the collector current is likely to vary. But in applications like amplifiers, the collector current should be maintained constant. It should not vary with the variation in these parameters. So therefore, it is possible only with the help of biasing circuit. So we have three biasing circuit: fixed bias, collector feedback bias, and voltage divider bias. So this last one is stable and it's the best biasing circuit. And the first one is simple but not stable. We'll see one by one fixed biasing circuit. So RB is the biasing resistance placed between VCC and base terminal. So in this case, the base current will be VCC minus VBE divided by RB. So current is limited by RB. But in this case, when there is change in temperature, beta also will vary, and ICB also vary, and that is not taken into account. And whenever there is variation in the parameters, that will not affect this current, and therefore this circuit is uh, not stable, and here the collector current cannot be maintained constant. The second one is collector resistor or voltage feedback biasing. In this case, RB is placed between collector terminal and the base terminal. In this case, the base current, it is given by VCC minus VBE divided by RB plus beta into RC plus RE. So here it is function of beta. So when there is any change in the beta, that immediately reflect in the base current. As a result, whenever the base current is changed, again the collector current can be maintained constant. Similarly, voltage divider biasing circuit. So a divider circuit is used here. So that is two resistors are connected in series, and the voltage developed across this resistance is applied between base and ground terminal. So here RTH is nothing but the parallel combination of these two resistances. So the lower one is R2, the upper one is R1. So RTH is R1 parallel with R2, whereas ETH is nothing but voltage across this terminal. So you can get this expression is nothing but VR2 will be equal to, see here. So VCC is this voltage connected across the two resistances R1 R2. So ETH will be equal to, that is total VCC into R2 by R1 plus R2. So with this ETH and RTH, we can write an equation for IB. IB is ETH minus VB divided by RTH plus beta plus 1 into RE. So RE is nothing but the emitter resistance. So here again, IB, it depends on beta. So whenever there is some variation in beta, that immediately it will reflect in base current. So because of changes in the base current, that collector current can be maintained constant. So bias stabilization. The stability of the system is a measure of sensitivity of the network to variation in its parameters. So if you want to say that it is stable, then that particular circuit have minimum variations with respect to change in the parameters. So here the collector current IC is sensitive to following parameters. For example, so I told you already beta increases with increasing temperature. So this will also affect collector current. So beta will be increasing with increasing temperature. VBE, so this also will affect the current IC. VB decreases about 7.5 millivolt per degree Celsius, increasing temperature. Similarly, ICO, reverse saturation current. This current is found to be doubled in value for every 10-degree increase in temperature. So these three parameters, beta, VB, and ICO, will change in temperature. And these three parameters in turn affect the collector current. So coming to the common emitter NPN transistors, this is the circuit. So VB is the voltage source to establish base current. at the input. So RB is the current limiting resistance. So this is the input circuit. VB is the voltage between base to emitter terminal. And in the collector emitter circuit, VC is the voltage and IC is the collector current, RC is the collector series resistance, and VC is the voltage across the collector to emitter terminal, and IE is the emitter current. So IC is collector current, IB is base current, IE is emitter current. So always you should know that in active region, the common collector base junction is reverse biased and whereas base emitter junction is forward biased. So coming to the input characteristics, it is the curve drawn between IB and VB. So this curve more or less, it looks similar to forward characteristics of diode. So here, when the voltage reaches the cut-in voltage, the device starts conducting current. So there are two curves here. One is for VCE1, another for VCE2. VC is nothing but collector to emitter voltage. So here VCE2 is greater than VCE1. So from this curve, you can say that if you're going to draw a horizontal line like this, when VC is increased, so you can say that more VB is required to produce the same base current. More VB is required. So for this curve, it is less, and for this curve, it is more. So as VC increases, more base voltage is required to establish current in the base terminal. Coming to the output characteristics, it is the curve drawn between IC and VCA, collector current and collector emitter voltage. So here, three regions are shown with cutoff region, saturation region, and active region. In the cutoff region, both base emitter junction and collector emitter junction are reverse biased. The active region, base emitter junction is forward biased, collector emitter junction is reverse biased. The saturation region, both base emitter and collector emitter junctions are forward biased. So in saturation region, the device will be fully conducting current. The active region is this region, and the cutoff region, this part. When the base current is made zero, the transistor will not be conducting current, it will be in the off state. So in saturation region, the transistor is fully on, and cutoff region, it is completely off. So here the curves are drawn for different base currents. So here IBN is greater than IB4, IB4 is greater than IB3, and so on. So if you're going to increase the base current, most likely the collector current also will be increasing. And let us see about DC load line. So we have to draw the load line and fix the operating point on this line. And mostly we will be using this load line to fix operating point when we are operating the transistor as an amplifier. So to fix these operating points, so this point corresponds to collector to emitter voltage equal to 0. And this point corresponds to collector current equal to 0. So here the base current equation is VB minus VBE divided by RB. And IC is, actually we can write it as VCC minus VCE divided by RC. This is written like this, minus VCE by RC plus VCC by RC. So VCE can be written as, that is VCE can be written as VCC minus IC into RC. So if you want to fix this point corresponds to, right, VC equal to 0. Substitute VC equal to 0, so you will get VCC equal to IC into RC. So IC will be equal to VCC by RC. So there is this point. And to get this point, you substitute IC equal to 0. You substitute IC equal to 0, you'll get VC equal to VCC. So this point. So this line. So you can fix operating point anywhere on this line and operate that transistor. Coming to the basic amplifier circuits, we have three configurations. Common base configuration. So here base terminal is common between input and output. So I is the emitter current, IC is the collector current. So this is input current, this is output side. So here alpha is nothing but output current by input current, IC by IE. This value it falls between 0.99 and 1. And this is called as current gain or current amplification factor. Coming to common emitter configuration, so the emitter terminal is common between input and output. The input current is base current and the output current is IC. The beta is IC by IB. So beta usually it will be greater than 100. So the current gain will be 100. So current gain is high as compared to the previous case. So further the beta can be written as IC by IB. So IC by IB is nothing but IE minus IC. This difference is nothing but IE. So further, if you going to divide this each term by IC, bring this IC to the denominator, you get IE by IC minus IC by IC. So IE by IC is nothing but 1 by alpha, and this minus of IC by IC is 1. So this you will be getting in the denominator. So this can be written as 1 by alpha minus 1 inverse. So further this can be written as alpha by 1 minus alpha. Common collector configuration. Common collector configuration. Collector terminal is common. So input current is IB, output current is IE. And here IE by IB is nothing but beta by alpha. And usually this beta by alpha is greater than 100. So further IE can be written as IC by alpha. And this further can be written as 1 by alpha into IC by IB. So that is nothing but beta. IC by IB is beta. Beta divided by alpha. So here the ratio of IE to IB is expressed in terms of beta and alpha. Coming to the comparison of various transistor configurations. So we'll see the following parameters for three configurations. So coming to the input-output phase relationship, for common base it is 0, that is both input and output will be in phase. Common emitter it is 180 degree, that is completely you will get the inverted output. So if you are going to apply a sine wave, so you'll get inverted sine wave output. So you're going to apply positive voltage, you'll get negative voltage. If you're going to apply negative voltage, you'll get positive. So complete 180 degree inversion you will get. And common collector there is no phase shift. Coming to the voltage gain, it is high for common base, it is medium for common emitter, and it is low for common collector. Coming to current gain, it is low for common base, it's medium for common emitter, and high for common collector. Power gain is low for common base. Power gain is to get the ratio of power output by power input. And similarly, common emitter, the power gain is high, and common collector is medium. Input resistance, common base it is low, common emitter is medium, and common collector is high. Output resistance for common base is high, common emitter is medium, and common collector is low. If you want to use transistor in a particular configuration, particularly for amplifier applications, so the input resistance must be high and at least medium, and output resistance must be low. So this condition, this configuration, right, this does not suit the requirement, so it is not used. Whereas this configuration is used for amplification purpose, and the common collector it's only used for impedance matching. Coming to the transistor terminal identification, so here the transistors are available in different packages. For example, you take this uh, metal can package. So there is a projection here. So the terminal which is nearer to this projection is called emitter. And if you are going to move in the clockwise direction, the middle one is base and this one is collector. Similarly, if you take the plastic package, if you just turn it upside down and so the left terminal will be emitter, the middle terminal will be collector, and the right terminal will be base. Similarly, you can identify the terminals for different packages. Coming to the H parameters, so we actually the H parameters will be provided by the manufacturers for a particular device. So if you want to analyze the transistor circuits, we need an equivalent model for the transistor. So to construct a model, we need these H parameters. So once we get an equivalent model for this transistor, we can construct the equivalent circuit, and by applying circuit theory concepts, we can analyze the current and voltages in the circuits. So the primary function of the model is to predict the behavior of the device in a particular operating region. So this is the given circuit. At higher frequencies, the C1, C2, C3, say they all act as a short circuit because the impedance will be very low. So this equivalent circuit at high frequencies, we have replaced the capacitors by a short circuit. So it is removed here. Similarly, this output capacitor also removed here, and this also removed here. It is shown as a short circuit. Since C3 is a short circuit which comes across RE, the equivalent resistance will be C. Similarly, these two terminals are connected to ground. So now this further can be drawn like this. So that is the input source and resistance. This one as is shown, and the equivalent resistance is RB1 parallel with RB2 is shown here. And here the transistor, we have to use the equivalent model here, and the output we have resistance RC. So input we are giving here, output we are getting here. So now this transistor small signal equivalent circuit. So this is the circuit. So we have to replace this block by this. So here the H parameters will be given in the data sheets. Even we can conduct some experiments and measure these parameters. So here, so between base and emitter terminal, that is input side, current is base current and HA is the H parameter, and here we have a voltage source equal to HRE into VC. At the output side, we have a resistance in parallel with the uh, current source. That is HOE in parallel, current source is HFE into IB. And the current in this circuit is IC and voltage is VC. Such parameters are useful in describing the input-output characteristics of the circuits. In this case, we are using this to describe the characteristics of transistor. So wherever it is difficult to measure impedance and admittance parameters, we can always uh, measure H parameters and we can construct the model. So the various parameters, H parameters are HIE is called as input impedance, its unit is ohms. This is input impedance. And HRE is nothing but reverse voltage ratio. There's no unit. HFE is also forward current transfer ratio. There's no unit. Whereas HOE is output admittance. So unit is same. So the formulas for parameters for various configurations are given. So here the first HIE and HFE, we can measure these two parameters by short circuiting the output terminals. Whereas the HRE and HOE we can measure by open circuiting the input terminals. So first parameter HIE, the short circuit output measure VB and IB, obtain this ratio. Similarly, for HRE, open circuit input, measure VB and IVCA, find this ratio. For HFE, again, short circuit output, measure IC and IB, get this ratio. This gives HFE. Similarly, HOE, so you open circuit input, find IC and VCA, and this ratio is called as output admittance HOE. Then one of the application of transistors, it is used as a switch. For example, this you take the simple circuit, yes, mechanical switch is shown here, a bulb and a supply. When the switch is closed, so the current will be flowing through the circuit and lamp will glow. If it is open, the current will not flow the circuit and the lamp also will not glow. So the same circuit can be constructed using transistor. The switch can be replaced by a transistor. So if here we have an NPN transistor, here we have a PNP transistor. So by applying control signal, we can turn on and turn on. So whether you are applying your low signal, NPN transistor will be in off state. When you are going to apply a high signal, so the transistor will be fully turned on. It will be operating in the saturation region. So the current will be flowing in the circuit and the lamp will glow. Similarly, in the PNP transistors, so when you are applying a low voltage, low signal, the device will be conductive. So when you are going to apply a negative voltage, the device will remain in the off state. So always when the transistor is on, it will be operating in the saturation region. When the device is off, it has to be operated in the cutoff region. So what you should learn in BJT. So you have to know about the applications. It is used as a switch and amplifiers, and almost in all electronic circuits it is used. And you have to know about the biasing circuits, different regions of operation, classes of operation, frequency response, such parameters, and important relationship of a transistor. So the VB is 0.7 for silicon. The emitter current is usually given by the expression beta plus 1 into IB, which will be nearly equal to IC. Since beta is very much greater than 1, this can be written as IC equal to beta times IB. Then coming to the power supply. So power supplies, basically it converts AC input into DC output. So we see the AC input is applied given to the rectifier. Rectifier rectifies this AC voltage. So this is the AC input and you get a rectified output here. So you can see here you get a rectified signal, both positive and negative cycles are rectified. So you get voltage of one polarity, but you have AC component. It's varying with time. So when you pass the signal to the filter, so this will reduce the AC component in the present in the output. So the AC component is reduced. Further, it is given to the voltage regulator. We can obtain a constant output voltage. So you know that voltage regulators are used in almost all electronic circuits. The purpose of regulators to maintain constant voltage irrespective of the change in the load current and load resistance, and also due to change in input voltage. So coming to the rectifier, so we have three types of rectifiers, half a rectifier. So here this is a circuit, we have one diode in the circuit and RL is a load resistance. When you are applying AC input, so only positive cycles alone it is rectified. So you get only positive cycles of the output. Negative cycles are not allowed to pass through the diode. So therefore, this circuit rectifies only half of the wave. Efficiency is 40.6%. Coming to the full wave rectifier here, we need a center tap transformer and two diodes are used, and this is the load resistance. So when we assume that during positive half cycle terminal A is positive with respect to B, that this diode will conduct current. Current will be flowing like this in the clockwise direction. So this terminal will be plus, this terminal will be minus, and this diode will not be conducting current. During negative half cycle, B become plus with respect to A. Therefore, this diode will conduct current will be flowing in the counterclockwise direction. Again, the current will enter here, leaves here. So polarity of the voltage will be here like this. So this rectifier circuit rectifies both positive and negative half cycles. So you'll get like this. So here, this middle line is nothing but average DC voltage. So if you're going to give this to a filter, you'll get this average DC voltage. The efficiency of this is 81.2%. Coming to the bridge rectifier, this bridge rectifier does not require center transformer. Instead, we need 4 diodes. So during positive half cycle, the red color diodes are conducting current. So current will be flowing like this through this diode and flowing through load resistance and through this diode and returning to the lower terminal of the winding. During the negative half cycle, this end will be plus with respect to this. So the current will be flowing from the lower end through this blue diodes, then through this resistance coming here, and then through this diode and returning to the terminal of loading. So in this case also, the circuit rectifies both positive and negative half cycle. So we get waveform like this. And efficiency is 81.2%. Coming to the bridge rectifier with capacitor filter. So here the only changes we have included capacitor at the output. So if you are going to add capacitor, so without capacitor, this is the waveform. So it has got AC component. If you are going to add a capacitance, so you will get like this. The dark line is the voltage. So that is charges and then discharges, charges and discharges. So you get a DC voltage and the AC component of voltage in this output will be less. So coming to the regulators, so we need regulator to maintain or to regulate the output voltage. So the output voltage will change due to change in the load resistance or due to change in the input voltage. In both cases, the regulator should give a constant output voltage. So here we have series and shunt regulators. This is a series regulator. In series regulator, the control element is placed in series with the load. So transistors the element. So it has series regulators have one or more devices placed in series with the load. Series transistors used to regulate load voltage. So here RS is the resistance connected between supply and Zener diode. This will be providing biasing current for Zener diode. And the voltage across the Zener diode is called as VZ. This voltage is called Zener voltage, and voltage between collector to emitter terminals is called as VB. So here the polarity of this voltage, polarity at this point with respect to this point is minus V. So the load voltage across load will be equal to sum of these two voltages, Vz minus Vb. So whenever load voltage decreases, so any decrease in load voltage, what will happen? The Zener cannot change, whereas this VBE will be adjusted. In this case, the VBE will increase and compensate for the decrease in the load voltage. And therefore, the load voltage will naturally, it will increase and it will be maintained. So a constant voltage will be maintained. So VL is nothing but VZ minus VBE. So the VB is regulated. So also you have to remember that whenever VBE is increased, collector to emitter voltage will decrease. Or when VB is decreased, collector to emitter voltage will increase. So here the output load voltage can also be written as this input voltage minus collector to emitter voltage. So whenever there is a variation in load voltage, accordingly the VC will be regulated. If PL is decreases, then VC is increased. How VC is increased, the base emitter voltage will reduce and this will increase the VC. Thereby, the voltage always will be maintained constant. So thank you. I hope you have understood all the topics covered in this presentation.